All right. Does that come out for y'all?
Yes, that looks good.
All right, awesome. All right, so I'm going to start talking about matching cognitive models to individuals. Um, Stupid mouse. All right. Um, so John Laird, I first heard the term coin of the realm from John for cognitive architectures. And it's a really neat idea. And and so the concept here is trying to figure out what motivates the different cognitive architectures to strive for at some level. And he talked a little bit about this earlier. So some architectures coin as fitting model data to human data, like John said, ACT-R, et cetera. Some architectures coin as functionality, SOAR, and some architectures coin as novelty. There are lots of architectures going for that as well. What I'm going to try to focus on here is a few issues with model fitting, particularly individuals, with the hope to kind of improve that particular coin. So we've actually heard several talks already about fitting average data from an experiment, or even fitting individuals. And that's kind of one of the standard ways that a lot of people do it. But we run the risk that no individual actually uses that particular strategy, even though the average performance may actually match that strategy. So we have a situation where you can have people who are doing one strategy and another group of people that are doing another strategy, and kind of average together, you can get average performance. And you model that particular strategy and nobody actually does it, which ends up being a strange cognitive model. Rob Siegler has some great examples in arithmetic and math learning for that. The explanatory sequence from Dave Keuris earlier today also talked a little bit about exactly how that actually played out. So the question I'm going to partially ask here is, how do we check if our model for an individual is actually correct, and how well does it fit an exact individual? We can also think about this as a specific problem, but problems give context as well. So some of that is simpler, some of it's harder, but I'm going to focus more on the individual. And there are lots of ways that previous people have done this. You could certainly do a parameter search for every single participant. This is used a whole lot in math models, math psych models. But one of the assumptions there is that it assumes the process is exactly the same or very similar for every particular participant. We have model tracing examples. You can model different strategies, but it can be kind of difficult to choose which path at the time. You can get divergence and backtracking. It's hard to do kind of a little bit of that in real time. We can also use tasks with relatively little variation, but those can be difficult to generalize. And we've even had a couple examples today. Dave Keuris earlier today was clustering participants based on how their data looks and then matching to strategies or mechanisms from his model, which is really cool. And then just a second ago, we saw Chris talk about matching performance to looked at models from stored models to get parameter estimates, which is also really, really interesting. What I'm going to try to do is I'm going to try to talk about a different approach here. So this is kind of, so I'm going to backtrack for just a second, but when John asked me to do this, he said, Greg, you can kind of almost do almost anything. It'd be fun if it were speculative, and it's fine. And so I took that to heart. So this is a speculative talk. It's brand new work, so I'd love comments on this. And so for what we're trying to do here is I'm going to kind of propose a way to model and fit model data to individual parameter data. It's kind of a 4-step process, kind of very loosely. So the first step is building strategy models that instantiate a specific strategy that you think may occur in your task. And I'm going to kind of give examples of this in a specific task. The second part is output process data from your model. The third step is to use some form of machine learning to learn the abstractions that exist within that model and within that particular strategy. And then the fourth step is to evaluate your machine learning model on a person's individual runs to identify strategy, and hopefully that will help what's going on with that. Help you identify and understand strategies as they play out over a particular task. Now, I will say that this should work for any model where you can actually measure and output intermediate results. If you only have just an answer and intermediate time, it's more complicated. Maybe you could do it, but I think right now that where we are is you want intermediate results. So what I'm going to do is I'm going to kind of show the task itself that we're working on here. And I'm going to show this method with a dynamic visual search and action task. Again, it should work for anything that has intermediate results. So this particular task is a supervisory control task. It's called Rescue. It's from Cummins and Mitchell. And you have essentially UAVs, unmanned aerial vehicles, like this. And then you have hazards, don't fly through these. You have targets that you're supposed to fly to. And then once you get to a target, you take a picture and off you go. And the goal is essentially you want to go to as many targets as you possibly can. The UAVs need periodic attention. The hazards change around. And people have to juggle a whole lot of things while they're performing this particular task. So they have to track the different UAVs. They have to make sure they don't need help. If they run into a hazard, the hazard hops on top of them or something changes. They have to get the UAVs out of the way. They have to reroute them. They have to remember which UAVs are likely to need help. You can have UAVs that need help concurrently, so life is more complicated at that time. You have lots of dynamic things going on. You're trying to do this under the constraints of human performance issues. And then you also, sometimes the automation flakes out as well. So the automation may not be performing correctly. You have to fix it if it doesn't. And this is kind of the simplified version of this. And it certainly requires some training here. So what I'm going to do is from that complicated task, I'm going to look at a single subtask here, essentially rerouting a UAV to a particular location, to a different location. And from an interface perspective, this is dead simple. Essentially, all the operator has to do is they have to right-click the UAV and then click on the destination. So it is as simple as you can imagine any other thing going on. It's not complicated. So what I'm going to do is I'm going to show an example of a skilled operator rerouting a UAV, and you're going to see eye movements tracked throughout. So the eye movements are kind of the bouncing ball, and I'll show this a couple times. All right, so this is kind of the UAV that you want to pay attention to. I think what you'll see is the operator rerouting it to this particular target here. So kind of what you saw, I'm going to kind of describe what you saw and then play it again. But essentially what you saw was the operator kind of looking around for a UAV to reroute, and then look for particular targets as well, and then try to figure out which one of these hazards was going to be in the way. They ended up making a non-perfect decision, perhaps, but again, it's a constraint satisfaction problem. This one may have had a clearer path, but it may also be further away, and so there's a time component here, etc. And so I'm going to show this again. See if this works. Yeah. And so notice that you see just a lot of stuff going on, even though the final interaction interfaces are actually pretty straightforward and simple. Okay, so in that particular 6-second clip, it's just 6 seconds, the participant searched for a UAV that needed rerouting, and they looked at just a whole lot of things, right? These are kind of the fixations that the eye tracker pulled out here. And it was variable, right? So now I'm going to kind of go back to my particular task here, where what we want to do to kind of get individual strategies out here. So the first step here is to build strategy models that instantiate specific strategies that you think may occur in your task. It's okay if you get some that are wrong. I'll show you kind of how to pull that apart in a second. So I'm going to talk about 4 different strategies, kind of a 2 different types of 2 different strategies. So you can imagine one possible example here would be a kind of a planning strategy where you search for a UAV that needs help. And once you find that UAV, you remember where it is, and then you search for a good target. So you're kind of trying to optimize something. And then once your target is found, you remember where it is, you go to the UAV, you right click it, and then you go to the target location and click on it. And it's kind of a full up planning, make things really good ahead of time. This is kind of the way that 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 perhaps an AI system would do it, perhaps and maybe people even do it at some level as well. You could also imagine an opportunistic version, which I'll show kind of briefly here. This is kind of the, you search for a UAV that needs help. You don't worry about where it's going to go yet, but you just select it, and then you search for a good target, and then you just select that one. And these are kind of both reasonable strategies. The opportunistic one has fewer memory needs, so that there could be an advantage there. But the planning may actually be, in some case, more effective in some ways. So that both of these are very much reasonable strategies. Okay, so that's kind of one set of strategies. You can also imagine crossed with that, another set of strategies that people use in dynamic environments, where they essentially observe the environment. They're not looking for something that's exactly task relevant. They're just trying to make sure that they understand the environment. This happens all the time when you are driving, for example, and you're tracking other cars. That particular car back over there may not be relevant to you right now, but it's good to know where they are in case your environment changes or they make some changes. So what we can do is we can build those kinds of models by having whatever model it is we're working perform these non-task subfixations while performing rerouting. So essentially we have 4 different strategies. These are just 4 of the many possible strategies. But we basically have a planning strategy and an opportunistic strategy. And then they're basically keeping track of the environment, or looking at the environment, is probably a better way to say it, and also for both planning and the opportunistic version. And then what we did is we built models of each strategy within ACTR. And we used an abstracted version of of Rescue here. I will also say that the version that we did use ACTR, but in theory, we should be able to use anything for this particular method. All right, so that was kind of step 1. Step 2 is we need to output process data from our model. And most of our cognitive architectures are able to do that. So essentially, each model has its own strategy to reroute a UAV. And of course, because it's a dynamic task, there's a fair bit of variability within each strategy. We have multiple different targets, multiple different UAVs, multiple different hazards. They're moving around, and different types, and everything just needs different amounts of help. So what we're able to do is generate relatively arbitrary number of traces of each model running in different random configurations. And the output, so this is the important part for us here, is that each model is able to generate visual attention, eye movements, mouse selections, etc., based on what it was doing at some level. Okay, so our third step here is we can use some machine learning to learn the abstractions that exist within that model and strategy. And so for us, what we did is we trained a convolutional neural network, a CNN, based on the ACTR model. And I think any sort of machine learning technique would use. We happen to use a CNN, and I'll show a little bit more detail about that in a minute. But essentially, these CNNs need a task to do in order to learn representations. The particular task we gave here was to predict the final target selection based on the preceding eye fixations and mouse selections. This is kind of, as you might guess, and as we saw earlier, a non-trivial task, because it's not just the last thing, the last target, the last object that the person actually looked at. It's not the most frequent thing that was looked at. Sometimes it's not even exactly what was looked at before. So it can be very difficult to make a strong prediction here. But that was what that was what the model actually did. And so the idea here, and this is the main part about what we're trying to do here, is that the CNN abstracts the key features of the model. And if the features it learns are correct, then it should do a good job of fitting or matching the empirical data. So that's kind of the primary piece here, that it's trying to learn some sort of key features so that it can then have a representation of it so that it can be used to fit it and learn it and predict it and classify it. Okay, so this is kind of a cartoon of our CNN. We started with the ACTAR model data, individual strategies, and I should say that we have these 4 strategies, and we had each one of these sets of model data. We took each of the 4 strategies individually, right? So we basically did this 4 times for each one of our individual strategies. So that's an important piece. We did not just have a single model that did everything, because we're trying to separate and understand the strategies from each model for the empirical data. And then we built a very standard convolutional neural network that we fed in the fixations and actions and additional fixations and every single action that occurred for a rerouting task. And then we have convolutional neural networks, and we have dropout and prediction and everything else. And the prediction itself is what target the humans is actually going to send the UAV to next. We don't give the network that information ahead of time. Of course, that's what it's trying to predict. And it's trying to learn some sort of representation, abstract the important features. That part is black box for what we're actually doing here. So as part of this, we trained the CNN for each of these 4 strategies we used. Again, these were individual strategies, individual models that were pushed through the CNN. Again, those strategies are the plan. There's one planning, there's one opportunistic, there's one planning with environment, and one opportunistic in environment. And so, if you could just think for a second which one you think individuals would use the most. And I've talked to a few people about that, and everybody thinks that that people are going to use some version of opportunistic, and some people are going to use some form of planning. So most people kind of hedge at some point in time, and they say it's a little bit of both, and that's kind of the next piece, right? So the last part here is to evaluate our machine learning model on a person's individual runs to identify the strategies. So essentially the way we did that, we were able to train our CNN, and we trained our CNN on ACTAR model data. And then we can do more with it in terms of what our empirical data is. So we extracted all the rerouting instances from every single individual operator. And we were then able to use the fixations and mouse actions to predict which target the operator actually selected. And we can measure that in terms of overall accuracy, and also accuracy for the individuals. I will point out, though, that this is not average data, right? This is the raw traces from every single individual, every single time they rerouted a UAV. And this is about 100 people, about 2,000 traces total. So, but this is really a key piece here, right? We're not averaging, we're averaging the performance of the individual raw traces. And that's a super important part about all this. So the assumption here is that, or the hope, is that an accurate prediction by the CNN suggests that the CNN had in fact accurately abstracted the features the operator used on that particular instance. All right, so we're going to expect some variability here for sure, because people are doing all sorts of things, and they might change strategies in the middle. They might we might have different people that use a strategy that we didn't program, all sorts of things. Okay, so the baseline, this is actually wrong. My chance is actually 20%. I evidently can't do math. And so chance is 20%. That's kind of, hopefully will be better than that. The best performance is about 75%. And the way that we kind of arrived at that is using a CNN to train and validate on all the empirical data. This is there's obviously 25% about what we cannot capture and don't know right now. And I'm happy to say a little bit about that a little bit later. But right now we're trying to match somewhere between 20% and 75%. That's kind of our goal. And this is kind of what we get. This is the planning, the pure planning strategy. And this is the planning and environment, and looking around the environment. And we see something really interesting here where the planning, the planning strategy itself is actually better than the planning in the environment. And kind of this makes some amount of sense as a post hoc explanation, but it makes some amount of sense where if you have a plan, you're not looking around at the environment a lot. And that is kind of in contrast to the opportunistic example. So for the opportunistic example, the opportunistic strategy, we have people that are, what's happening here is that the opportunistic strategy is rather worse than the opportunistic plus the environment. So in this case, what's happening is that if you take the opportunistic, is that when you're using an opportunistic strategy, you're much more likely to be searching for the environment for non-task related things. So this is kind of a neat way to think about this that kind of emerged from that. And again, these are the individual, so just to recap really quick, what we did is we took the planning model, the planning ACT-R model, and trained it on the CNN, and then took that particular, and then looked at all of the empirical operators to see how well the CNN was able to predict their particular performance. Okay, so, and this is kind of this next part, this is kind of the last part here of what I'm really excited about, but we can also run the models to classify what strategy operators used over time. So we ran the top two strategies here, the planning and the opportunism and the environment. And we can look at strategy change over time. And the following graph is kind of a single operator, so there's no averaging. I'm just trying to understand what happened on this specific individual operator. And we see something I think is I'm really excited about this. So essentially in the first half, this is the first half of we have different sessions. So this is the first session and the second session, essentially, after a fair bit of training. And in the first session, people are using more of an opportunistic plus environment strategy compared to just a pure planning strategy. And in the second half, that completely reverses, where the opportunistic and environment strategy is used much less and the planning strategy is used much more. The way that I'm interpreting this is that when you're first, they're still learning this task. They're pretty good at it at this point in time, but even in the first half, after a fair bit of practice, they are still in the, oh shit, there's a lot of stuff going on here. And so they're kind of they're doing a lot of opportunistic, I got to do this, I just got to do it as quick as I can. After a fair bit of practice during the second session, they can take a little bit more time. Things have slowed down mentally for them because they know a bit more about what they're doing, and they can use more of a planning strategy here. Okay, so this is my very last slide. What we've done here is we've combined the cognitive process models with some machine learning models, and it's allowed us to be able to track individuals as they perform tasks, and that's what I'm really excited about, and I hope this kind of new method might be able to differentiate and improve models, especially at the strategy level and especially at the individual level. And that's all I've got. Thank you very much.
Thank you, Greg. We do have a couple of questions.
Awesome.
The first question is, how do you know you've selected the right breadth of strategies to reflect the variety found across individuals? Are the CNN features sensitive to the precise balance of different strategies it is trained on?
Okay, so the first part of that question is, I don't. We have to make our best guesses, and it can certainly be an iterative process. And the kind of the four strategies that I talked about were not, I think most people would come to some version of planning and opportunistic, and then you look at a dynamic task, and you start finding that really quick that people are looking at the environment. There certainly could be other strategies that are available, and but there's no guarantee for that. The other piece there is that we're at 70, I kind of talked about the 75% maximum there. And it could easily be that we're missing some form of strategy there. If you look at that particular 75%, there, most of the missed strategies there seem to be, they seem to fall into one of a few categories. One, the strategy is just very, very difficult to extract what the person was actually doing. And the second one was where we had unusual eye tracker instances. That is, the eye tracker, the person never actually looked at a target. And so it's really difficult when there was no instance at all of what the target was actually chosen. And that's just gonna happen sometimes. The second question was, how do we actually know about that the CNN has abstracted the right features? And again, it's a hope. That's why this is a new method that I hope people will actually give a try. And it's, a lot of the CNNs are black boxes in many ways, and it's very hard to get real understanding from what they're actually doing. And I would expect that there would be a lot of overlap between some of the features that people are that we actually train with the 4 different models, but they're different enough to give different results.
Thank you. Another question, do you anticipate different models may describe different levels of expertise in a human operator?
Yes, absolutely. I could totally imagine building a novice model and an expert model of something like, the Tower of Hanoi, where you do in fact get intermediate processes there. And I could completely see where you could focus on the strategies that people are using and then match that and look at a fine-grained analysis where you could see novice to expert transitions on any number of these particular strategies. I think that's a really exciting idea.
Thank you. Can the CNN generalize to new situations, or would the ACTAR model need to be rerun and the CNN model retrained if substantially new situation is encountered?
I think that's a great question, and I'll say I don't really know how well it can generalize. If I had another dynamic task, I was trying to do this, I think I could actually get some generalizability. If I were going to, for example, let's say I wanted to use this in a car driving task, I would prefer to have generalizable. I prefer to have something else where I could actually look at car driving, the specific tasks. But I think that if I only had partial data, or if I had an incomplete data there, I could get at least kind of close. I think that's more of an empirical question, and I'm kind of hedging here because I think it's really hard. But I'm hopeful that if we generate some of these micro models for strategies, that we could in fact use them across. We could identify strategies in other tasks without having to rewrite the full ACTAR model. That would be brilliant.
Thank you so much, Greg. There's a lot of other questions in the chat.
Oh, fabulous.
To answer those and ask those offline.
Okay.
But now get ready for our next speaker, Shivali Mohan.
Thank you very much.